The power of the train comes from the rotary motion, with a few exceptions. In steam and diesel engines, the reciprocating motion of the piston is converted into rotational motion. The faster a device that generates power through this rotational motion turns, the more power it can extract. In the case of an electric motor, the reason is simple: output is a value obtained by multiplying torque by rotational speed, so a higher rotational speed results in a smaller torque. A major factor in determining torque in an electric motor is the strength of the magnetic force. The magnetic force is determined by the current flowing through the coils wound on the motor and the number of turns. If only small torque is required, the current can be reduced or the number of turns can be decreased. As a result, the magnetic force generated is weakened, reducing the amount of iron core required to utilize it efficiently. Electric motors are made of iron and copper for efficient use of electromagnetic force. Copper has long been used in electrical equipment that carries large currents because of its low electrical resistance and fairly reasonable price. However, copper has a specific gravity of 8.93, making it heavier than steel, which is a disadvantageous material for weight reduction. Steel is also heavy, with a specific gravity of 7.8, and a reduction in the use of these materials will be effective in reducing weight. Recent expectations for electrification of aircraft have led some to use aluminum, which weighs only 1/3 as much as copper, instead of copper to reduce coil weight. However, the dilemma is that aluminum has about 1.6 times the electrical resistance, and to compensate for this, the coil wire must be thicker. Converting to aluminum helps to reduce weight, but does not solve the problem of increased size. On the other hand, high-speed rotation also effectively reduces the amount of iron core required, which accounts for around 60% of the total weight of the electric motor. In the 1950s, when Japan National Railways was rapidly electrified, electric motors for both trains and locomotives were an extension of pre-war designs and had low-rated speeds. The MT40 series used in the 80 series had a rated speed of 870 revolutions per minute at full field magnetization and approximately 2,000 revolutions per hour near maximum speed. The MT42 used in the EF58 was rated at 705 rpm for 1 hour and approximately 1500 rpm near maximum speed. Moreover, the insulating material's weak heat resistance prevented operation at high temperatures, limiting the amount of current that could flow through it. Therefore, in order to obtain the necessary magnetic force, a thick power wire had to be wound around a thick iron core, and the electric motor had to be large. With the rapid economic recovery after the war, Japan National Railways was required to provide high-speed mass transportation. To haul long trains at high speeds, more powerful and lightweight locomotives were needed, and the electric motors had to be smaller and lighter as well. Leading the way was the EH-10 test locomotive for high-speed operation, shown in other videos. The electric motor used in the EH-10 was the MT43, but its basic design was in line with the pre-war period. In order to enable 120 km operation, a significant weight reduction was required to reduce the track load, and a newly designed electric motor, the SE-174, based on post-war technology, was developed. The hourly rated speed under full field conditions was increased from 800 to 1000 revolutions per minute, and the maximum allowable speed was as high as 3000 revolutions per minute, which is sufficient for high-speed tests. However, high-speed operation with locomotive-hauled trains required significant track improvements, even on the Takeda main line, raising expectations for power-distributed trains, which are easier to make lighter. Innovations in electric motor mounting methods have also had a significant impact on the high performance of trains. Instead of the suspension drive, which was the mainstream at the time, the bogie-mounted type, which could drive stably even at high reduction ratios, was adopted, and the electric railcar system rapidly gained attention. Under such circumstances, new designs of electric motors for railcars were also introduced, based on post-war technology. The MT46A used in Kodama-type trains is rated at 1,860 rpm for 1 hour in full field condition, and is normally used above 2,500 rpm when running at high speeds. With the addition of high-temperature operation made possible by advances in insulating materials, the output per unit weight of the electric motor has doubled compared to the Series 80 era. Thus, the golden age of high-speed electric railcar with low track load was ushered in. Although some improvements were made later, the technology at that time was standardized and widely used for a long period of time. Although innovative electric motor technology was not adopted in JNR trains for a long period of time, technological development continued steadily. The technology is the application of AC motors. As shown in other videos, AC induction motors were considered the ideal electric motor and attracted much attention in the 1950s, and various attempts were made. However, rapid advances in semiconductor technology for power applications will turn this dream into reality. The availability of induction motors will revolutionize the speed of electric motors. The structure of brushes and commutators was no longer needed in electric motors, allowing them to rotate at high speeds without worrying about sparks, commutator failure, or wear. Moreover, since there are no windings on the surface of the rotating part of the motor, there is almost no need to worry about the problem of strong centrifugal force associated with high-speed rotation. In other words, it is an electric motor whose rotational speed is limited only by the durability of the bearings. An example that illustrates this change well is the change in the weight of the main electric motor for the Shinkansen. In the Series 0 era, the main electric motor weighed nearly 900 kilograms at 185 kilowatts output. When the output was increased to 230 kilowatts in the next generation 200 series, it still weighed 825 kilograms, despite advances in weight reduction technology. In the Series 300 prototype, the first induction motor-driven car, the output was increased to 300 kilowatts, but the weight was halved to 456 kilograms. This evolution is astounding, and more than the elimination of the brushes and commutator itself, the ability to increase the rotation speed from 2,900 revolutions per minute to 3,825 revolutions per minute has had a profound effect. It became the norm for electric motors to turn in excess of 6,000 RPM at high train speeds. This technology contributed greatly to the lightweight, high-speed Shinkansen trains that followed, and to conventional trains in terms of weight reduction. Weight reduction has been steadily progressing in electric vehicles due to the higher speed of electric motors, but what about non-electric vehicles? The reciprocating steam engine is still the most representative of the slow-speed engines. Steam locomotives even appeared with large wheels, over 2 meters long, to compensate for the slow speed of the engine, but their high center of gravity made them impractical. There was also a device to use a small-cylinder steam engine with multiple cylinders to achieve higher speeds, but it could not overcome maintenance and slippage problems. The use of turbines, which can rotate dozens of times faster than a piston, may reduce the size of the power extraction system, but steam engines, which require large boilers, do not benefit much from this. Eventually, the development of electric motors and internal combustion engines gradually eradicated steam-powered systems from railroads, and the various innovations with steam engines never saw the light of day. What about diesel engines, which have replaced steam engines and are rapidly gaining power in the railroad industry? Initially, diesel engines had a speed comparable to that of steam engines, but by the time they became popular in the railroad world, the speed had increased to nearly 1,000 revolutions per minute for locomotive use. Even JNR utilized it for diesel trains and locomotives. For diesel railcars, the maximum RPM was already as high as 1,800 RPM with DMH17, and there was no dramatic change in RPM after that. On the other hand, for large locomotives, medium-speed diesel engines were initially imported, followed by the adoption of high-speed diesels. The DF50 was produced by importing an engine from Germany. The engine alone weighs 7.6 tons and generates 1,200 horsepower at 900 RPM. The DD91 was produced, also with an imported German engine, which is a high-speed diesel with 1,500 revolutions per minute and potentially 2,000 horsepower, yet weighs only 8.6 tons. In terms of output per weight, the DD91 engine produces nearly 1.5 times more power than the DF50 engine, and it appears as if the difference in RPM is directly attributable to the difference in power output. Even for locomotive engines, this is the practical limit of RPM, and for diesel engines, which must operate at high pressure, it was extremely difficult to achieve power output at high RPM. The low-speed nature of the diesel also affected the power transmission system. Some attempts were made to take advantage of this low speed by replacing some of the cylinders of the steam engine with diesel cylinders, but this did not become popular. There is a difference between the electric and hydraulic transmissions, which have since become mainstream, and whether they turn a generator or an oil pump turbine, but the higher the rotation speed, the more compact both of these types can be. Therefore, the electric transmission, using a medium-speed diesel turning at about 1,000 revolutions per minute, had to be paired with a heavy, large generator. Later, the DC generator was replaced by an AC generator, which reduced the weight slightly but kept the same RPM. This was one of the reasons why electric power transmission systems were disliked in areas where only weak track structures were available. To overcome this problem, there was an attempt to reduce the weight of the generator by using one engine to turn the rotor and another engine to turn the stator in the opposite direction, effectively doubling the number of revolutions. However, only the generator can be lightened by this method. Therefore, it is less effective, and this method did not become popular either. The hydraulic drive, on the other hand, was more serious. Power could not be transmitted efficiently at the normal speed of the diesel, and it became commonplace to drive the turbine pump after increasing the speed with the speed-increasing gears. Low-speed rotation is a disadvantage of the electric drive, but when combined with a turbine engine, this problem is solved in one fell swoop. But this time, on the contrary, the rotational speed was too high, and for a long time, the technology for making generators with high-speed rotation could not keep up. Even when steam turbine locomotives were being tried in various ways, the turbines were mated with reduction gears to slow them down and turn the generators. When converted to a gas turbine, the rotational speed becomes even faster, and a cumbersome reduction mechanism must be included to drive a typical generator. In the TGV gas turbine prototype, gas turbines totaling 2,200 kilowatts drive an alternating current generator at 4,000 revolutions per minute. The generator weighed 4 tons, far heavier than the gas turbine itself, but dramatically lighter than a diesel generator. At this time in Japan, the conversion of the Kumaha 591 to an electric gas turbine car was considered in an attempt to find a solution to the problems posed by the mechanical drive of the Kiha 391. In the 1990s, high-speed rail once again became the focus of attention in the United States, and push-pull gas turbine trains were planned. Bombardier was commissioned by the Federal Transit Administration to build a prototype 5,000 horsepower jet train. Called the Advanced Locomotive Propulsion Systems Project, the University of Utah will be responsible for developing the Flywheel energy storage system and high-speed generator. This was a government-led project that was also part of the development of a short-time high-power supply system for electromagnetic catapults and railguns. Once both were completed, a hybrid gas turbine locomotive with a direct-coupled high-speed generator would be born. However, due to political considerations and other factors, the high-speed rail project itself was abandoned and the jet train project was cancelled. Although flywheel energy storage systems were later used in electromagnetic catapults, they were never used for locomotives. In the 21st century, Russia developed natural gas-fired gas turbine locomotives, and the first vehicles with a generator set driven directly by a gas turbine were put into practical use. With the exception of Russia, trains equipped with these gas turbine direct-coupled high-speed generators have never been used on a full-scale basis on railroads, but in recent years they have suddenly become the focus of attention in other fields. It is the aviation industry that calls for the electrification of airplanes. Many have realized that the current batteries are still insufficient for use in airplanes, and that electric gas turbine hybrid drive is a realistic solution for all but the so-called flying car class, which is designed for short distances and has a capacity for only a few passengers. Major aircraft manufacturers are planning to develop mid-sized airplanes based on this system, and Honda, which became famous for its Honda Jet, is also actively developing small airplanes based on this system. An ultralight power generation system using gas turbines and high-speed generators, which has not blossomed in the railroad industry, may one day blossom in the aviation industry.